Welcome back everyone to Petroleum Downstream Crash Course. Today we are going to explore real-life designs of crude oil desalters. So for that we are just going to look at examples of old patents, and this patent is 244-60-48. This patent was published in July 1948. It was filed in November 1946, and the inventor is Mr. Blair Jr. It looks like. His signee is Petroleum Corp, and then of course you find your export. You can export the citations using these links described here. So we've already downloaded the patent. So let's take a look. This is figure 1. Now, figure 1 is talking about introducing fresh oil with a chemical demulsifier, and there'll be hydrocarbon here along with fresh water. And then it goes through some squiggly thing here. Not too sure what that is, but we can go take a look inside the actual patent itself. So this will be a mixer settler system. Brine comes out. Okay, the brine comes out. So the brine comes out, and the oil, basically the organic layer, it goes out the top, and the hydrocarbon is extracted, and desalted oils will come out the bottom. Alright, so that's figure 1. This is figure 1. So let's go to figure 2. Charles M. Blair Jr. Alright, so this is the inventor again. So this is figure 2. Only this time, instead of putting in the chemical demulsifier first, as was the case in figure 1, see the chemical demulsifier goes in first. Instead, the hydrocarbon goes in first, goes into this box thingy. I'm not sure what that is. This looks like a heat exchanger. We can check that out later. But after that, you inject water directly into the oil and hydrocarbon mixture. So oil and hydrocarbon get mixed with fresh water at this point, just before 5A. So this will be a valve, I think, and chemical demulsifier will be injected before this coil thingy and into this mixer settler system, which is 7A, and brine comes out the bottom and hydrocarbon comes out the top. The salted oil comes out the bottom of the separator, labeled 9A. You see here, highlighted. Okay. This is another figure. Okay, so this is figure 3. Figure 3 is basically this. So crude oil goes in with a demulsifier, injected along with hydrocarbon, and then is injected into some sort of fractionating tower or some sort of splitting tower, where the brine comes out the bottom and desalted oil comes out the top. So fresh water looks like it's injected from the top, or rather you can see the valves here between 16 and 15. You see where the fresh water is. Just to your right will be 16 and 15. The valves are here. So what this network of system does, 16, 15, and just to the bottom of 15 you have 21, 20, and then 14. Now 14 is where the oil and water mixture can go in. Now you can see this, what do you call that? This valve system, 15, 21, and 20, that allows for you to control where the water actually enters the tower. Okay, so that's just a rough idea. Let's see whether there are any more figures. Alright, so we are at the beginning of the patent. So this is a US Patent Office, the patent number 244-60-40. This is a process for desalting mineral oils. And the names of the inventor are here. The name of the inventor is here. Then this address, blah blah blah. It's a Petroleum Corporation Limited, Wilmington, Del. I don't know what that is, but it's a corporation of Delaware. Okay, so this is just our information we don't really need to bother about. Okay, so let's take a look. We'll zoom in to the first part. So this invention relates to the removal of water-soluble impurities from crude oils, such as salt. It has the main objective blah blah blah. So what is being highlighted here basically is they're talking about the objective of this invention, which is basically to remove dissolved inorganic salts, basically salt from petroleum, top petroleum oils. This is what do you call that? Long residue. This is long residue, top petroleum oils, crude fractions obtained by distillation. So any of the distillation fractions, and extremely viscous petroleum oils which are not readily desalted by other methods. So basically, this invention is supposed to cater to very viscous crude oil, okay, which are very thick. So as you know, today the API values of oil tend to get lower and lower. So as they get lower and lower, the tendency for them to be thick is higher. So you probably need very good desalters like these that cater to that kind of viscosity. Okay? So from line 9 to 20, I think, the second paragraph. The production of crude oil is blah blah blah. Okay? So what this is saying is that, okay, if I usually produce crude oil, there will be some brine that comes out of it, and such brines are usually emulsified in the crude oil, meaning to say they are trapped in the crude oil. And, okay, this sentence says, yeah, the emulsion will come out. Alright, so let me just summarize these two sentences, what's highlighted in blue. So basically what it's saying is that usually the salt water and oil will separate out, but at other times they will continue to mix in what is known as an emulsion. Okay? So this is saying there is a certain upper limit on how much water is, or brine is salt water, how much water and salt is really tolerable inside crude oil. Okay? So, if the oil is properly treated, they call it dehydrated oil or pipeline oil. Okay? So the water, blah blah blah. So what this sentence is saying is that, what do you call that? The sentence says that basically the salt content is low enough so that I don't really have to bother about all my what do you call that? I don't have to bother about corrosion because my equipment is able to handle it. Now, this probably describes the motivation for desalting. However, in many cases, in the great majority of cases, or in many cases, the residual emulsion contained in the pipeline oil does not consist of pure water, but is an aqueous solution of inorganic salts, which was originally produced with the crude oil when it emerged from the ground. So they're saying that yes, it is mixed with the water originally, and it has been found that such salts are very objectionable to the refiner. Okay, this is basically telling you why you have to desalt your crude oil. So let's move on. Okay, you can see the first few paragraphs are actually talking lots about the motivation for inventing a machine like this, okay, such as the desalter. Alright, so this paragraph, line 44 to line 52, says the presence of such inorganic salts. Okay, so this just tells you the possible detriments of salt in the crude oil. So they're saying the plugging or fouling of heat exchangers, decreased heat transfer, increased replacement costs, accelerated coke formation, lower quality products, lower use of valuable products, and greater labor requirements. Basically, increased costs, and you're gonna have more trouble in your refinery because of the increased salt content. Again, it further emphasizes why you need a desalter. So here they start talking about the past efforts to remove salt from the petroleum. So let's go to the second part. This is the second column. It might appear that this could be accomplished by methods commonly employed for the treatment of ordinary emulsified oil in the field. So what this is saying is that, yeah, I already have, though there are already methods to deal with the crude oil and saltwater emulsions, but you probably need something else. So this is the something else, or this is the reason why something else exists. So, however, the conditions obtained in a refinery where salt removal operations can be carried out are different from the oil field, as originally produced. It's dehydrated too. Okay, what's this about? Let me read and I'll explain it to you. In the latter case, the emulsion may contain the blah blah blah. In the average perhaps as much as 24 hours or more, whereas the refinery okay, what it says here is that you have an upstream process, alright? The upstream process where you produce and drill oil out of the ground. So when you drill oil out of the ground, the throughput or the amount of oil you have to desalt and process is generally less. However, in a refinery, you're processing so much more barrels of oil per day, so you need your settling time to decrease, or basically more settling time, which is the time that the water and oil layers separate. It means you need a larger vessel for the oil and water to separate. Okay? So blah blah blah, I'm not going to go through this. This is important. Furthermore, this is blah 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 blah. Okay, that's it for the first page. You can see that in the first page of this patent, it's telling you about the background and why this whole highlighted part. It's just telling you about background and why this desalting process is important, and why do I need to invent another machine, why I need to invent another desalter, despite there already being many other desalters available commercially at that time, which is 1948, I believe, or 1946. 1946. Yeah, you can see here. So in 1946, there may have been other processes to process the crude oil already, or rather to desalt the crude oils, but that was insufficient for the refinery. So this explains the reason why you need to develop a whole new process for desalting crude oil. Okay, let's move on to the second page. Let's zoom in again. So the train of thought that this guy is trying to say, or the train of thought this guy is trying to bring us through, is that basically you need a higher percentage purity and you need it faster in the refinery inside the crude oil in the refinery. Alright. Let's take a look just to be sure. Oh, okay. Anyway, what was missing in my previous explanation is that when the oils were drilled out of the production plant, there was some desalting processes already carried out to make it available to pump it into the pipeline. So that's pipeline oil, or oil that's usually shipped to you. However, there's still some salt in there that's not going to be good for the oil refinery. So you still have to remove the residual bit that the earlier desalting process wasn't able to get. You're supposed to get rid of the salt that the original desalting process wasn't able to get rid of. Okay? Yeah. So anyway, yeah, that's just motivation again. So here they're telling you to get out the residual percent. So okay, let's put it in numbers. You have a crude oil that you drill out of the ground. Maybe it contains 3 to 4% of water and salt content. So to make it available for the pipeline, you want to push it down, right down to 2% or 2%. That's the first desalting process to make it available to pump in the pipeline. But to put it into the refinery, you need to reduce that way more. So that's in the ppm range, right? That's less than 1%. Okay. So the difficulty of getting the remaining 1% and less is due to the reasons highlighted in blue here. Okay? So you can read up more. I'm not going to go through everything. Now it'll take horribly long. So it says that yes, it's extremely difficult to remove the last 1/10% or so of emulsified brine for petroleum oil by any common means of demulsification, be it mechanical, electrical, or chemical. Oh yes, yet the amount of inorganic salts carried when even 0.1% of emulsified brine may be much more than enough to cause serious difficulties in the refining process. So basically, you need to desalt it even more. Alright, so this guy goes on talking about mechanical procedures, and then it says why these mechanical procedures fail. You can see in highlighted in blue. So the other method talked about is the electrical dehydrator, which was talked about in the earlier videos. Okay. So what does it say? It's employed in the resolution of emulsified oil to separate the prepared emulsion of predetermined water content, as previously described. In many instances, the electrical dehydration process is satisfactory, but involves the added expense of the electrical dehydrator. So yeah, so it talks about pros and cons of this dehydrator. So this is yet another method. Okay, this is another method. It's called chemical demulsification. chemical demulsifier as seen highlighted in blue here. So chemical demulsification is used in the resolution of roily oil or cut oil, roily oil, whatever, yeah, followed by a settling period to permit the sedimentation of water particles. So they are saying that this is a very simple step. No expensive apparatus may be purchased, no much skill or attention is required, but it's still unsatisfactory. Little or no separation takes place within the limits of refinery economy. What this statement is saying is that it doesn't happen fast enough, so it's not so good. Oh, this is what, yeah, it's just saying it's not happening fast enough. By fast enough, they mean you need it within 2 hours to settle out. This is true for various reasons, blah 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 blah. Okay? So it's true for various reasons that, but there's one reason alone which is sufficient, and that in order to maintain the chemical demulsification, you must usually heat the oil, and to prevent the loss of heat, it's necessary the oil be transferred to the furnace and fractionating still without delay. This is diametrically opposite. Sorry. Opposite the practice which is usually employed in oil fields. Okay, so this whole paragraph talks about the need for heat integration. So basically, you want to heat up your oil to distill it. Or perhaps when you want to demulsify your oil using chemicals, you need to heat it up to a certain amount. Just like the electrostatic ones, which require about 90 to 150. But if after you heat it up to 90 and 150 degrees, you don't want the oil to cool down, because then you have to spend extra energy to heat it up again. Okay? That is not, it says that in the upstream or oil production, that is not so important. Okay? But when you talk about refinery, you have to conserve heat, because that adds up to your cost really quickly. Okay? You have to conserve heat, so integration of heat. So you don't want your oil to cool down like halfway after you desalt it, and then you go and distill it. So as soon as you desalt it, you want to distill your crude oil. Okay. So this is yet another page of why you want another desalter. See, the author spends a lot of time justifying why a new desalting process is needed. So he goes on to say, I've discovered that crude oils are particularly difficult to desalt by the previous processes. So these include the very viscous crude oil, the low API crude oils, the reduced crudes, which are long and short residue, and the petroleum fractions of high viscosity, particularly dark-colored oils with viscosities greater than 4 centistokes at 200 degrees F. Refer to the ExxonMobil chart. 4 centistokes at 200 degrees F. So that's an heavy gas oils and vacuum gas oils. So the heavy gas oil and vacuum gas oil, which means the light vacuum gas oil and heavy vacuum gas oil, all fall into this category. So because of this high viscosity, there's something has to be done. Because with high viscosity, the settling time is way too long. Because the water droplets take forever to fall through thick oil, as compared to very easy to flow oil. Alright? So, okay, let's just review. The object of this present invention to overcome the difficulties existing in previous desalting processes. And he says that I have found, quote unquote, such heavy oils may be desalted satisfactorily by diluting it with low viscosity oil. Basically what he's saying is that if the oil is too thick, use thin oil such as diesel. You can dilute that oil with diesel to lower the overall viscosity so that the the oil can settle faster. So he outlines what the procedure is like. You add a chemical demulsifier, add the hydrocarbon diluent to reduce the viscosity, and so you have a thorough mixing of hydrocarbon diluent, oil and demulsifier, addition of water. So you have, let's just review, demulsifier, hydrocarbon, and you mix them up with the oil, and now you add fresh water to the hydrocarbon oil system containing the demulsifier, and followed by dispersion of the added fresh water to the oil mixture. Provision of gentle agitation. Agitation. Remember it talked about electrostatic agitation. So you're going to vibrate those small little water particles or water droplets within the oil so that they coalesce or join together. Provision of a quiet settling sufficient to permit settling out of the coalesced brine and fresh water. So just giving it enough time to let the water settle out of the oil. So in some instances, the original heavy oil may contain no brine particles, such as, especially in the case of reduced crudes, we found that the salt contained in the oil is a solid dispersed phase of salt crystals, especially since the original water may have already been evaporated. So what he's saying here is that in the case of long and short residue, where you have already passed the crude oil through the distillation towers, the vacuum and the atmospheric towers, they're saying that all the water may have already been evaporated off, which is kind of logical given that you're subjecting the oil to over 300 degrees C of temperature. So that makes sense. So once the water is evaporated, the salt crystals are left. So in such cases, if you still want to desalt the reduced crudes, the long and short residue, you have to do like what? You have to add fresh water, you have to add to dissolve these solid salt particles to form a brine. Then the chemical demulsifier must also be added. So this is the detailed process, blah blah blah. So it's outlining what the invention is about here. So here he talks about the temperature limits 100 to 400 F. Which is slightly like, what do you call that? About 40 degrees C to about just under 170, I suppose. That's a give and take estimate. So, okay. You're saying the high temperature is better. I think that's describe essential features. Blah blah blah. Such a diluent should be obviously telling us about his thought process, yeah? I mean, in this one, this is his thought process. Okay, such a diluent should be completely miscible. Examples of such situation. Okay. Alright. That's so much. So he spends 1.5 pages talking about why his invention is so important and why you need to invent it. So blah 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 here. Oh, sorry, here. So here you are talking about the various diluents available to reduce the viscosity. And they're saying the LPG fraction will not be suitable as a diluent. And for practical reasons, you probably use something like gas oil, which is diesel. So diesel qualifies because it has a viscosity of less than 4 centistokes at 200 degrees F. It is suitable. Say his own preference here, but okay. So we might be talking about gas oils also. Okay. On after, I'm not sure. You can take a look at that again. So here he goes on and on, rambling about all the details. This one. It says that LPG. Okay, sorry. So earlier I was saying that the LPGs wasn't suitable. It's saying that ethane and methane are not suitable. So these are the lightest of the gases. And it's saying stuff like butane, propane. These solvents have low viscosities. Okay. And they have been found to give particularly satisfying results. Okay, so that is good. Then he gives the reasons why they are good. Oh my goodness, wow. Yes, it's a very detailed patent. Okay, then he goes on into some really technical things like Reynolds number. If you study fluid mechanics, you should be quite familiar with what this is. But if not, don't worry. I'm not going to cover it. He's just going through all the engineering thought processes. That's 10 columns worth already. This is good for engineers to know, right? But you can go read it up if you have your own time. I'm not going to go through all this. Okay? The 10th column. You see column 10? Column 10 is here. Column 10. You finally get him explaining to you. How the demulsifier works. So let's zoom in again. Okay, look for these bold numbers. Note to self, look for bold numbers. Everything else is just explanation why he had to design it, why he had to what do we call that? The motivation for his invention. Okay, so in figure 1, oil is heated in a heat exchanger. The diluent hydrocarbon oil is heated by passing it through the heat exchanger into the crude oil stream at any desired point. Okay, blah blah blah. So that's what I explained earlier. Similar. Added fresh water is dispersed. For the water globe valve, this is just a valve. So it talks about Reynolds number, just ignore that. This agitation is carried out in apparatus 6. Okay, so what is apparatus 6? Let's take a look at here. I'm looking at figure 1. So we know what this squiggly line is now. Apparatus 6. As you can see on your screen, it should be in the center of your screen, apparatus 6. So this squiggly line you see in the center of the screen is an agitator. It's basically a mixer that is supposed to mix up the water and oil. It's the same as you pouring water and oil into a plastic bottle and you're shaking it up really badly. So that's what number 6 is. Number 6 is the mixer part. Number 7 is the settler, where the brine and the oil layer are separated. Let's scroll back down, back to page 10. I'm going to be there for 60 seconds. Settler is number 7. A colorless water particles settle at the bottom of the separate brine phase. Clean desalter, blah 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 blah. Okay. Figure 2 depicts a similar arrangement, just that the order of mixing is different, as shown earlier. Such an important feature at present in invention, provision of successful method for countercurrent extraction of salt from oil. So that's figure 3. Crude oil is containing chemical demulsifiers warming exchanger 12. So exchangers number 12. Take a look. These are exchangers, heat exchangers. Okay. Scroll back down. Heat exchanger 12 mixed with warm hydrocarbon diluent through valve 13. It enters vertical column 11 through line 14. It goes outward countercurrently with the water, which enters column 11. Passes through heat exchanger 16. Water level is maintained. So these are a lot of details. A lot of details. A lot of thought processes, this guy. So the details, the timing and everything you can go and read. But what this figure 3, what he's saying is that figure 3, this is a countercurrent, what do you call that, settler. So what happens here is that the oil, which is rich in salt water, is pumped through the bottom and it floats to the top, and the water comes from the top and it goes to the bottom. So when it goes countercurrent, the mass transfer is very efficient. Basically, when water goes down, it gets more and more salty because the oil is going up and the salts is getting transferred from the oil to the water. So that's actually a liquid extraction. If you ever studied chemical engineering before, you know what this is like. So this is basically liquid extraction at work. Alright? So this is a settler system. Okay, so this is the desalted oil and the brine, salt water. And of course, once the... So this is, what do you call that? That will be what 7A is like. Because the oil and brine will be in here. Then the desalted oil and hydrocarbon, that will be, what do you call that? Separated in column 9. So let's look for 9. So it says 9 is a still. A still is a distillation. That's why it's called distill. So the still is here. So this is basically a distillation column where the salted oil comes out the bottom and the lighter hydrocarbons are being boiled off. Okay? So that's basically how the desalter works. You can see according to these figures here, the real life designs by this guy, C.M. Blair Jr.